So, in today's lecture, we take an example of what we have done in case of material balance, for stage wise processes. We will solve this example by both graphically as well as writing down the equations. Okay, so essentially we will take a very simple example. We will have one stage, two streams getting in, and with certain specs of the feed, and what concentration we want to bring down the levels from one to another, and see how much is the solvent requirement. And then we will extend the same example for multi stages. So, we will have 3 stages, and we will answer the same question, how much is the solvent requirement to bring down the level of say raffinate phase from one level to another phase. Okay. Our idea is to understand what we have learned when we wrote down the expressions for material balance, how we can solve, how we can address the same problem by graphically, by graphs. Okay. So, let us take this example. Again we will focus on binary components. So, let us say we have a fluid mixture, a mixture of A plus C, okay, and we call this R phase, raffinate phase, and we have a solvent, we call it B, and we want to remove this C, this component from one level, say this A plus C. Let us put some flow rate here. So, the flow rate is 1000 kg per hour, okay, and it contains 15% of C, weight by weight basis. So, W by W, and we have been asked to separate C using this pure solvent B. So, B is a pure solvent, and we have to separate C say by 95%, which means we remove C in this component A plus C, in this mix feed A plus C, if we call it feed R phase, by 95% using this solvent B. Okay. And there are two cases here. A, we have single stage, and B, we have 3 stages. So, these 3 stages are co-current cross flow, all right, what we did in the very beginning of this section of the course. And we also assume ideal stages. So, all the stages are ideal, and if you recall, we said ideal stages means these are equilibrium stages. So, talking of equilibrium, we have been given that y equals 3.75 x as equilibrium relationship. Okay. And very important to note that this y, it reflects the concentrations of solute in solvent. So, this is actually C by B, solute free basis. So, we are using this capital X. So, this X is C by A in the feed or R phase. So, this is your R phase, and if you recall earlier nomenclature, this is your E phase. So, two streams A plus C R is brought in contact with B, and equilibrium is given by y equals 3.75 x. Note, this is not y equals mx or a small y and x, small the small fractions. This is solute free basis. This is C by B, not C by C plus B or C by C plus A. Here we use this x and y, etc. So, this is all solid free basis, and we have already seen if we use the capital Y and capital X, we have operating curves which are linear. So, let us go back again. 1000 kg per hour of feed contains 50% of C. We have been asked to remove or reduce by 95%. Okay. And the question is, how much is the solvent requirement? solvent requirement in both cases. So, how much is kg per hour etc. is required. Okay. So, we draw the schematic here. Example 1, we have this stage 1, first example, this feed consisting of A plus C or R phase is brought here. It has mole fractions. Okay. So, x0 is a fresh feed x0, and since feed contains 15% of A, and so the solid free basis mole fractions should be 150 divided by 850 or 15 by 85. Okay. So, this is your 0.1765. So, these are mole fractions solid free basis. We have R as given as 1000 kg. So, this would be A plus C, okay, but we are working on solid free basis. So, RS is 850 kg. In other words, this is a solvent 850 kg. So, this is your only A. C is the transferring component. Transferring component. We bring in this contact with pure solvent ES. There is a question, what is ES? It is a fresh fluid, pure. So, Y0 is 0. After treatment of this A plus C, we have the treated fluid A plus C. Now, the mole fraction is x1. And what is x1? We were told that component C, transferring component, now it reduces by 95%, which means if we have 150, if we are starting with 850, so x1 would be 150 by 850 into 0.05. So, 95% of C has been removed. So, we are using this solid free basis 850, it is a solvent RS, and we have 150 of in the beginning here C. So, we have removed 95%. So, that means 5% is left. So, we have 0.05%, and this number is 0.00882. Okay. And this stream, now we have another stream here which has mole fractions Y1, and this is your ES. So, ES will remain the same because we said it is a solid free basis, and Y1 is unknown here. How much is the mole fraction concentrations here in the exit phase here. Now, of course, we can write a material balance. All right, it is a very simple example. We can write a material balance. So, RS, the feed which enters here, x0 minus x1. So, this is what is removed C, and it is gained in the second phase ES, Y1 minus Y0. So, note here x0 is greater than x1 and Y1 is Y0, because this phase picks up the transferring component or diffusing component C here. So, of course, a very simple problem, everything is given here, RS is known, x0 is given, x1 is given, okay. Y0 is 0, and we have ES, which is, the question is how much amount of ES is required. Okay. So, this ES is unknown, and Y1, which is the mole fraction of the exit concentration, is also unknown here. So, what we have done here is simple material balance, in equal to out. All right. So, in equal to out, we make a species balance or material balance, species balance for this diffusing component C here. We assume that A or B, they do not transfer from one stream to another stream when they are brought into this stages here, cascades. So, now we have two unknowns, all right, Y1 and ES. What is the mole fraction of the solvent phase or E phase at the exit of this stage, and how much is the solvent requirement. So, we are looking for one more equations, and now here comes the thermodynamics. All right. If you recall the question, we said that these are ideal stages. All it means, the two streams when they are brought in contact, they are well mixed, they spend infinite amount of time theoretically, or we say that they spend good amount of time, so that when they make an exit, they are in equilibrium. So, which means y and x at the exit, they would be related by this equilibrium relations which we wrote earlier, y equal to 3.75 x. So, we have one more equation here, y equals 3.75 x, okay, and y equals 3.75 x, it is applicable for the exit y1 and x1. So, we know y1 and we can write as x1. x1 is known to us 0.00882. If we substitute here, we get y1 which will be equal to 0.0331. Now, we know y1 and we can substitute here in the previous species balance to obtain the amount of ES, very simple algebraic, to obtain 4306 kg per hour. So, this is all kg per hour here. Okay. So, it was a very simple problem. Two streams brought in contact, they spend good amount of time there, so that the exit concentration are in equilibriums, and we have been asked to determine the solvent requirement. We wrote down the species balance, whatever is transferred from E phase or from R phase goes into this E phase, raffinate to extract phase, all right. And then we write down the expressions, we apply the equilibrium independent equations for the exit concentrations y1 and x1. Then we have two unknowns, two equations, we have solved it. So, very simple, but more important here is, let us see what is our understanding graphically. Okay, the by graphically also one can solve, and then we can mark those points, equilibrium points, operating points, what we have done earlier, operating line, etc. That gives us a better understanding of the physical problems, because the same approach you will like to apply, you will like to extend when we have multi stages. Theoretically, you can solve graphically, or you can solve writing down the equations, algebraic equations for a species balance, for equilibrium curves, how many unknowns we have, how many variables are there, and then you can solve it. So, it is up to you how do you solve it, right. In some cases, it is better to work graphically to get the faster answer, or for the physical understanding. Sometimes when the graphically we are unable to obtain, then we solve mathematically writing down the algebraic equations. Very often in some cases, if the problem becomes more complicated, one has to resort to the programming, Fortran, C, etc. All right. So, it is up to your choice, depends upon the type of the problems. So, let us try to understand the same problem graphically. So, what we have, y and x, capital Y and capital X, all right, and the equilibrium curve was given to us, y equals 3.75 x. All we do, we plot this. So, now the equilibrium curve is this, y equals 3.75 x, where 3.75 is the slope of this curve. So, you can plot graphically. Okay. Let us mark down the points, go back to this stage again. We have two streams getting in here, y0 pure solvent is 0, and this is x0 which is given to us. So, 1 0 0 we can mark it here. So, this is x0 and y0 is 0 here. So, this number x0 we know 0.1765. So, that is a mole fraction, solid fluid basis in the feet. Okay. Exit, we do not know this y1, we know this x1, and x1 we said it is 0.00882. So, we can take 0.00882, all right. So, let us see, this is x1 is 0.00882. So, we know this point. Of course, we do not know y1. Now, there are two ways, or the same result you will get. We know the flow rate here Rs, okay. We do not know this flow rate Es. If we know Es, we can obtain y1. If we know y1, we can obtain this Es, okay. But now we know that y1 and these two streams, they are in equilibrium, because we assume it is an ideal stage. So, two streams which are living, they are in equilibrium, which means if we know x1, we can mark this, we know immediately this y1, which we did earlier also. So, we can take a pencil or graph scale and you can obtain this y1. If you connect y1 and x0, we will get a slope here, and this slope is nothing but, if you recall, this is Rs over Es, all right. So, graphically it sometimes is easier to solve. You take x1, you know the equilibrium curve, you mark this point, connect this, we have Rs by Es. Once we know the slope, Rs is known, we obtain Es same as before. So, I leave it to you as an exercise to check you obtain the values of Es similar to what we obtain by writing down and solving this material balance equations. So, it is a very simple example. The more important to realize that y1 and x1, they are in equilibrium here. If you know x1, you can mark E1. Suppose the same problem says that we know the amount of Rs and we know the amount of Es. Graphically, all you will do, you will take the slope, it is a cross current. You are adding it here, write down the material balance, you will get this negative slope here with negative. If you write down the equations as y equal to mx plus c, you should convince yourself that we are getting a negative slope. You mark the slope, extend this till the equilibriums, you will obtain y1 to obtain the mole fraction of exit concentrations of this Es phase, of the solvent phase. Okay. So, again, it does not matter graphically or about algebra right now, the algebraic equations, but more important is trying to understand and mark what is happening in the stages here. Now, let us get to the second stage, second part of the problem, where it says if we have taken our 3 stages. Okay. So, now we have one stage, two entering streams, 2 exit streams. Okay. We bring in contact with the second stage. Now, in the second stage, again we add a fresh feed. Again you treat it ideal stages, 2 exit streams are in equilibrium, take this treated stream from the second stage, bring it to the third stage, and there again you bring in contact with the fresh fluids. So, how much is now the solvent requirement? Rs1, Rs2, Rs3. If it is assumed that we have equal solvent flow rates, so how much is your 3 Rs in comparison to single stage which we solved just now. So, the idea is still the same, our feed is A plus C here, and we want to reduce the 95% of C in A plus C streams by using 3 stages instead of 1 stage, and we will see how much is the difference in the solvent flow requirement. Again, one can solve graphically and one can solve writing down the equations. So, let us draw the schematic and see how we can solve the same problem by 2 methods. Okay. So, here we have now 3 stages, 1, 2, and we have 3. So, in this is y0, x0. So, we have y0 and we have this x0. Now, we have stage 1, this becomes x1, this is stage 2, this becomes x2, and we have 3, this becomes x3. And every time in all the stages we bring the fresh solvent. So, all this y0 same equal to 0, and we are assuming we have the same flow rates, which is Es, and Es. So, we have now y1, we have y2, and we have y3. And before we solve, it's given that all 3 stages are ideal stages, which means y1, x1 are in equilibrium, y2, x2 are in equilibrium, y3, x3 are in equilibriums. X0 is given to us same as before, 0.1765, and x3, the stage from stage number 3, the stream which comes out from stage 3, this concentration is also given 0.0082. So, these two are the same as before. Flow rate same as before, 850 kg. So, this is also given, this is given, this is given. Y1, Y2, Y3 they are not unknown. ES, ES, ES are also unknown. Y0 is 0 and we have been asked to solve, determine the solvent flow requirement. ES plus ES plus ES or 3 ES equal to what, and compare to the previous values which we obtained as 4,306 kg per hour. So that's the problem. One can write down the material balance or species balance for all 3 stages. Okay, so let's write down the same balance which we wrote, right? So what enters from the first stage is RS, okay, RS x0 minus x1. This will be same as if we write down the second equations which we had for the second stream, which is ES y1 minus y0. So that's a stage 1. Okay, we can write down the same for stage 2. RS will not change. This is solid free basis solvent. So solvent flow rate will remain the same. This will be RS. Now this would be x1 minus x2. So this is second stage. This will equal ES. We are assuming ES1 is same as ES2. So we don't have another subscript here. So this is ES, and now we have Y2 minus Y0. This is stage 2. Similarly, we write the equation for stage 3 as RS x2 minus x3 equals ES y3 minus y0. So stage 3. And now we should identify how many variables we have which we are supposed to determine or unknown. Look at this, all we know is only x0 and x3. We don't know x1, we don't know x2. We do not know the solvent flow rates ES. We do not know y1, y2, y3. All we know, we have y0 pure solvent entering every stage which is at pure, so 0 concentrations. So we have 3 unknowns and we have 3 equations. So we require 3 more equations. Okay, so 6 unknowns and 3 equations. And then if you recall, we have those 3 equations assuming all these stages are ideal. So when they are ideal, the exit concentrations, they are in exit streams, they are in equilibriums. Okay, so y1 is in equilibrium with the x1, or y1 and x1, they are decided, they are governed, or they are related by this equilibrium curve. Similarly, y2 x2 and y3 x3. So we have actually 3 more equations assuming these are all ideal stages. So if they are ideal, now we have y1 equals 3.75 x1, y2 equals 3.75 x2, and y3 equals 3.75 x3. Now we can say that there are 6 unknowns and 6 equations. 6 unknowns and 6 equations, right. Of course, now the problem is well defined, but you must understand that if we substitute y1 in terms of x1, okay, y2 in terms of x2, y3 in terms of x3, and then you try to solve this as an exercise, you will see that this is non-linear here, right. You won't be able to solve directly. You will have to require iterations. If you again try to substitute x1 in terms of x2, you will see, you will get in quadratic equations. All right. Now, of course, the problem is well defined. We have 6 unknown, 6 equations. This can be solved, but the more important here to note is that we should also be able to solve graphically and see where is this linearity or non-linearity business here. The operating lines are linear, equilibrium curves are linear, okay, and we know the 2 concentrations x0 and x3. All we know that living streams, they are in equilibrium. we should be able to mark these lines on the graph, on the equilibrium curves, operating curves, and see how we can solve it. That also improves our understanding of the problems which we have here. Okay, so let us solve the same example by graphically. So now we have this equilibrium curve here, y, and we have x, and this is our equilibrium curve, y equals 3.75x. Now this is given to us x0, which we said this equals 0.1765. Let us start from here. So this is x0. We know Rs, right, but we do not know Es. Es is not known to us. That means we cannot draw this operating line which has a slope of minus Rs over Es. Okay. And the streams which two streams which we leave the stage 1, this y1 and x1, we know they are in equilibrium, but we do not know y1 nor we know x1. So this point is also not known to us. So this would be, if we know this point, if we can mark, this would have been y1 and this would have been x1. So we do not know this Es here, right. So we do not know the slope, nor we know y1 or nor we know x1. These are the intermediate points. All we know the exit, finally x3 is here, which we said x3 equals 0.00882. We have been asked to reduce the concentration from mole fraction from x0 to x3, but we do not know the flow rate Es nor we know y3. So all it means, one has to make this iteration. It's a trial and error. Trial and error. See, we are experiencing the similar type of problems what we faced earlier when we try to solve mathematically. All it means, we will assume, one has to assume some slope here, assume slope, or assume Es, okay, which we have been asked to find out. Take this slope, we get this concentration x1. Now the second stage, again we are bringing this stream in fresh contact with this fluid, which is y0 given to us 0 concentrations. Now if the amount is same here and here, that means we will get the same slope. So assuming some values of Es, we draw this slope, we get y1. We know y1, these two streams are in equilibriums, y1 and x1, they are in equilibriums. So we can mark this point x1. Again we can take this slope here. Note that this line will be now parallel to this, because the flow rate of the solvent in the stage 2 is same as before. So this slope will also be minus Rs by Es. So now we reach here. This point is, coordinate would be y2, stage 2, and this is y2 stream, and this would be x2, which is here. So we get this point here. Now we start third stage and we draw the same parallel lines with the same slope, minus Rs over Es, to obtain y3 and x3. All it means, if we have marked this point 0.082, we have not reached the same point. That is why we said it is a trial and error. One will have to readjust the slope here, or will have to readjust the solvent flow requirement to reach 1 through 1 to 3 stages, this x3 what we want here, right. Or alternatively, one could have done this way also, assuming x3, now we know y3, we could have gone backward and to calculate this Es to obtain this x0 point here. Either way this will work, but more important to note here is that this is a trial and error problems, which you will encounter whether you solve graphically or you solve by writing down these equations. There also you will have the same encounter problem. You will have to assume some values of Es, etc., to solve those 3 equations. All right. the more, and also to important note that these points we have been able to mark. This is the operating line, this is the equilibrium lines. We realize that two exit streams are in equilibrium. So, y1 x1, y2 x2 and y3 x3, they are on the equilibrium curves, coordinates are on this equilibrium curves. Okay. And if you do this, one can obtain, and to show that the amount of ES, I leave this as an exercise, that amount of ES in this case will be much smaller, than in the previous case, which is single stage. Actually, the total amount of, so 3 times ES, because we are assuming that all 3 stages they have the same flow rates. Here the amount of solvent required will be much smaller than we have in case of single stage here. I leave this as an exercise to solve graphically as well as by mathematically writing down the equations. So we have taken this, we took this example, very simple example. The idea was to make a simple material balance, a species balance, or write down the equilibrium curve, see how many unknowns we have, how many equations we have, right. So that the problem is well defined. Simultaneously also try to solve graphically, or at least mark those points that this is entrance stream, this is the exit streams, what is the raffinate concentrations, what is your extract concentrations, leaving stage 1, stage 2, stage 3. If the two stages are in equilibrium, if the stages are ideal, then the leaving streams will be in equilibriums and those points will be on the equilibrium curves. So, although this example was very simple for 1 stage or 3 stages, the idea of this example is your own understanding, physical understanding of this mass balance or this equilibrium curve, right. Now we take 1 unit operations one by one. So, if you recall in our first lecture, we said that there are 4 unit operations which we are going to discuss very rigorously. One is absorption, distillation, extraction, adsorption and the drying. Okay. So, these are the 5 unit operations listed for this course, okay, mass transfer 2 here. So, we take this absorption, the first unit operations. Okay. So, now when we say absorptions, essentially we have a gas phase. Okay. Gas phase is brought in contact with this liquid phase. So, let us take an industrial example. We have a power plants which emits sulfur dioxide or carbon dioxide, certain pollutants into atmosphere, and EPA, agency like EPA, all right, environmental agencies, they say that the emissions cannot exceed certain level. In other words, sulfur dioxide in this flue gas from the power plant cannot exceed, let us say 0.1% or 1000 ppm, right. So, all it means, before we emit or before we exit this gas, this has to be treated by water or by certain solvent, appropriate solvents. Okay. So, that is absorptions, a gas phase brought in contact with a solvent, liquid phase. So, 2 phases, and for simplicity we assume we have a binary phase. So, air and sulfur dioxide. So, air is one fluid, of course it contains oxygen and nitrogen, but we have one fluid, air and sulfur dioxide, 2 components, and it is brought in contact with water, which may be fresh, pure water, but when sulfur dioxide it absorbs into it, water does not evaporate, for simplicity, all right. So, this would be the most simple example of absorptions. We have been given a continuous packed bed column. Okay. We talked about 2 different ways by which 2 streams can be brought in contact. Generally, we have absorption column which is a continuous packed bed. So, we do not have trays or cascades, right. The example which we took in just now, it was a stage wise cascades. So, generally applicable in distillation column or applicable in extraction. So, now we have a continuous packed bed in which gaseous phase air is brought in contact with water, and we will see how do we go about it, which is how we can make a material balance, species balance, how do we draw the equilibrium curves, operating curves, how much is the stage of the height of the column, how much is the diameter, what is the diameter of this column. So, these are the process design or process variables which we are in. So, we begin the first unit operation, absorption. So, we have two phase, gas plus liquid, and we have two components. So, we have say H2S, example sulfur dioxide, or say carbon dioxide in air. So, we have two components, one component is air and the other component is, let us say, sulfur dioxide. Okay. It is brought in contact with the liquid. So, we have some solvent H2O, or say KOH, or say we have some ethylamine, etc. So, this is one component, and when sulfur dioxide is at job, we have this sulfur dioxide. So, this is a component sulfur dioxide which diffuses from air or gas phase to this liquid phase. So, this is absorption, and you can imagine that if this liquid is saturated with the gas, we can also have desorption. So, it is a reversible process, absorption slash desorption. Desorption is also known as stripping. So, the principle of absorption or desorption or stripping is similar. Okay. So, this is what we are trying to address here. Let us draw a column. And we call it packed bed column. So, we will discuss the configuration of different type of packing. All we are seeing right now, it is a packed bed column. This air containing sulfur dioxide is brought from one end. So, we can again mark some concentration here, mole fraction, let us say this is Y0. So, for the gas phase we use Y0, flow rate is given, say Gs. So, again solid free basis, sulfur dioxide free basis, flow rate is say given kg per hour or standard liter per minute, or we can have certain cubic meter per hour, etc. Flow rate is given, say 1% or 0.1% of sulfur dioxide in atmosphere. We have been asked to reduce this concentration to Y1, say 0.0001% before this goes into atmosphere. To do this, we have been given a fluid, one of these fluids. So, it is a liquid, one of the liquids as a solvent. So, this is solvent. So, this liquid is given, and we have been asked to reduce this concentration from Y0 to Y1. So, this liquid and gas, the way it is shown, now it is in the counter current arrangement, counter current continuous contactor. We can also have co-current, but this is the most common and most advantageous. We discussed earlier that counter current continuous contactor has large driving force, larger than co-current. As a consequence, the height of the column is smaller in this case. So, again we will come back to those details later. Let us say that we have this packed bed column. So, here we have some kind of packing, we will discuss this also later. So, these two streams are essentially brought in contact, counter current direction, opposite directions, and then this gas is treated, and then it makes an exit after the concentration is so much reduced, and the liquid concentration changes, say pure solvent if x0 is approximately 0 or x1, right. So, for the end here y1, this is x1, and here this is y0. So, we have this x0 here. Okay. Now, let us start with, before we get into the detailed design or write down the operating balance, if you recall, we have to establish the equilibrium. So, we are talking of absorptions from gas phase, certain species is transferred into the liquid phase, sulfur dioxide from air into water. Okay. So, there has to be an equilibrium curve. In other words, given pressure and temperature, water cannot take sulfur dioxide in excess of certain concentrations. Water cannot take ammonia in excess of certain concentrations. Ethylamine cannot take H2S in excess of certain concentration. It is decided by thermodynamics, equilibrium, right. These are all equilibrium curves. So, we have to get back to the literature and get our what you call solubility data or certain equilibrium relations, which will tell us given so much of concentration in the gas phase, how much maximum or how much equilibrium concentration we have in the liquid phase. That is equilibrium, right. Given y, how much is x. Given partial pressure of gas sulfur dioxide in one stream, how much is liquid phase concentration, mole fraction in the liquid phase. That is equilibrium curve. Okay. So, we get into some Perry's handbook or McCabe-Smith or Treball's handout or appendix, and we note down the equilibrium curves, equilibrium data points, and one can plot here. But it is also important to note that there are two very common theories or laws which are used or which have been used to determine this equilibrium relationship. One, if you recall from your knowledge, maybe stoichiometry you have done or mass transfer 1, is a Rawls law, okay. Mostly for ideal solutions we apply, and the second is Henry's law. So, these are the two common laws one can use to determine the liquid phase concentrations given the gas phase concentration. Let us note down this. So, we are discussing now equilibrium curve, okay, because this is our starting point here. So, we are trying to obtain or we are starting from here. Given partial pressure in the gas phase, say certain millimeter of mercury, how much should be x? So, Pg versus x or x versus Pg, mole fraction of gas in liquid phase. Okay. Mind you, this Pg can also be written in terms of mole fraction y in the gas phase. If you apply y Pt equals Pg. So, where Pt is the total pressure. So, either you could plot y versus x or Pg versus x, and essentially you have some curve like this. Given total pressure Pt and temperature, let us say we have a curve for sulfur dioxide. All it means, given so much of partial pressure in sulfur dioxide in air, how much will be mole fraction x in the liquid phase. One can also, instead of x, one can also write in terms of C, moles per cubic meter of the liquid phase. So, different ways of writing these concentrations, okay. Either y versus x, capital Y versus x, Pg versus small x, or Pg versus concentrations, different ways of writing all these equilibrium curves here. Idea is that given pressure and temperature, such data are known to us from certain handbooks or from certain calculations. Similarly, we will have different curve for ammonia. Similarly, you can have a different curve for HCl. So, these are the diffusing species or transferring species or the species which absorbs in certain solvent. So, solvent maybe it is water, we said it may be KOH, maybe H2SO4, etc. So, given pressure, given temperature, we have a system of solute versus solvent, and this is, and we have the data, or we have some equation y equals some function of x or Pg as some function of concentration, etc., or we have been given this equilibrium curve or some plot, equilibrium plots are known to us. Either way we can plot, or we can, given the plot, we can determine, we can calculate those mole fraction, etc. The idea is simple. We have gas here, this is a liquid phase, certain species transfer from one phase sulfur dioxide from here to here. This is y, this is x, this is capital Y, this is capital X, this is small partial pressure here, small pz, and here we have this x, etc. So, these are all your equilibrium curve, we starting from here. And as you said earlier that there are two very common laws. If it is an ideal solution, then very often one can calculate as P equals partial vapor pressure at the given temperature into X equals Y into P. So, this is your Rawls law. Rawls law can be applied to calculate mole fraction in liquid phase given mole fraction in gaseous phase, etc. If we know the total pressure and if we know the vapor pressure at this given temperature here. If the solution behaves as non-ideal, one can also apply Henry's law, P equal to Hx. So, this would be your Henry's law, okay, and generally Henry's law is applicable for dilute solution, P equals Hx or some form y equal to mx. So, one can also make calculations, but generally all these data are available from literature, and that becomes a starting point for our calculations. Okay. Now, there are certain design considerations. Okay. So, one is of very important is the choice of the solvent. Now, this sulfur dioxide, H2S or ammonia, it is possible that we have several type of solvent. So, when you design, okay, when you say process design, you have to consider what type of solvents or what choice you have for the solvent, okay. And the choice of solvent that also requires several other considerations: cost, availability. Once you have treated your effluent gas with certain solvents, then you have to worry about the disposal. You have the spent liquor and how you are going to spend it. So, safety considerations, right, disposal considerations, economy also play a major role in deciding what type of solvent we have. So, again we do not focus on those aspects. We assume we have chosen a certain solvent and we have the solute. We refer to certain literature data for the equilibrium curves, and that becomes our starting point. But let us note down for your educations design consideration as far as the solvents are concerned. So, choice of the solvent, of course, the first should be the gas should have very large solubility, significant solubility. So, that is the first choice. If we choose water, we should have a very large solubility for sulfur dioxide or for ammonia. The second is volatility, right. We do not want our solvent to have very large volatility, okay. The solvent we do not want to waste. So, it should have less volatility, or we can say less vapor pressure. It should not be very expensive. So, cost consideration is another. Availability should be readily available. Safety, that is a major consideration here, because safety plays a major role in handling or during handling. Okay. Our gases or the liquid should not be corrosive, because if it is a corrosive, then material of constructions accordingly for the pipes, etc., or the equipment, right, material will become itself major bottleneck in the design. Viscosity also plays a major role, because it is a question of transport in the pipeline, right. So, these are some of the design considerations one has to keep it in mind when you are choosing a certain type of solvent. Well, that is not the orientation of this course here, when I am sure you have the design course at some level, okay, where you look at the cost part of it or economy part of it. Okay. So, right now in this course we are concerned with mass balance, species balance, equilibrium, drawing the operating curves, what is the solvent amount of solvent required, how many stages we require if you have the stage wise contact, how much is the height of the column if it is a continuous packed bed column like we have here. Okay. So, these are the things we are going to focus in this course.